So here is a ladder problem that I want to do, and it will be just a video, just the ladder problem by itself. So we have a 3-meter long ladder, and it leans against a frictionless floor, against a frictionless wall, rather, at an angle of 60 degrees. So you have a, let's see, you have this. This is the ladder. Okay. And this angle here is 60 degrees. Let me just make sure I have it right. Yes, it is 60 degrees. So we want the ladder not to slip. So first of all, so that means the net force has to be 0 and the net torque has to be 0. Here's the x direction. And here is the y direction. The forces on the ladder are, it's leaning against the wall. The wall is frictionless, so it doesn't apply a force parallel, but it applies a normal force. Let me call this one here normal force from the wall. And then the ladder is being pulled by gravity at the center of mass. So right here, there is the mass times gravity, the mass of the ladder. They didn't give us the mass of the ladder, so it's probably going to cancel. The wall here, the ground will apply a normal force this way, a normal force from the ground. And then what else? The ladder wants to slip this way, so we need the force of static friction this way, which makes sense. Because if you have just the normal force from the wall, that's a net force to the right, you have to have a net force from the left, a force from the left to cancel that. So we say the net force in the y direction has to be 0. That's requirement for static equilibrium. The net force has to be 0 in both the x and the y direction. And so in the y direction you got what? Two forces. The normal force from the ground, let me call them NG looks like MG. Let me call this one N1, and let me call this one N2. All right, yeah, I think that's better, less confusing. So N1 is upward and MG is downward, so I get N1 minus MG has to be 0. That means the normal force N1 has to equal to just MG. Okay. MG. All right, next. The net force in the x direction has to be 0. The x direction has to be 0. And so we get in the x direction we have N2 to the right, that's positive, minus the force of static friction to the left, that's negative, equal to 0. Now, if we've reached the static friction, the force of static friction, then we're at the maximum force of static friction. It means that the force of static friction, let's see, the force of static, so this equation will give us the force of static friction equal to N2, okay? And the force of static friction is related to the normal force, and it's equal to mu s times the normal force, the maximum. So if we reach the force of static friction, max will equal to mu s times the normal force that it makes with the ground, and that is mg. And 1, which is equal to mu s times m times g. All right, we're done with the forces. I need to do the torques. The sum of the torques has to be 0. Okay, the sum of the torques, what are they? Well, there is the torque due to, well, we have to choose a point of rotation, by the way. A good point of rotation would be here. You can choose it again, here or over there or way over there or anywhere. Choose it cleverly, choose it here. Why? Because I have two forces right at the pivot point here. If I choose this to be the pivot point, that gets rid of the torque contribution from this one and this one, because both are here. So the distance from those forces to the pivot point is equal to 0, so there is no torque contribution due to them. So the torque due to N2, torque due to the normal force from the wall, N2, would be N2 the force, times the distance from here to here, which is the length of the ladder, which I'm going to call L, the length of the ladder, times the angle they make with the sine of the angle that they make with each other, which is this angle here. Right, R is a vector that points from the point of rotation to where the force is applied. So this angle. So what's that angle? Well, if this is 60, this is 60, so this is 120. And the sine of 120 will be the same as the sine of 60. Yeah, the sine of 120 is the same as the sine of 60. So this is, let me write it as the sine of, let me make sure it's 120. Yeah, this is 60, 180, yeah, 120. Sine of 120 degrees. And let me just do that. Sine of 120, I think it's radical 3 over 2, sine of 120. Yeah. Yeah, radical 3 over 2. So N2 times L times radical 3 over 2. That's N2. And N2 is equal to the force of static friction. So let me write it as the force of static friction. So the torque due to N2 will be the force of static friction, radical 3 over 2 times L. That's the torque due to N2. Let's get the torque due to N1 and then the torque due to the mg. Okay. The torque due to mg will be, how far is mg from here? That's L over 2. Oh, I'm sorry. This one is trying to cause a clockwise torque, so that will be negative. That's a negative sign. The mg is this way, so it's trying to rotate it counterclockwise. That would be positive. I forgot to do that. So, yeah, note the minus sign here. Minus sign, a minus sign. So you have mg times L over 2, the distance from here to the mg is L over 2, times the mg, the mass of the ladder, times gravity, times what? Well, they make what angle with each other? R is from here to here, it points in that direction, so it makes this angle with it. So if this is 60, this is 30, this is 150, so it will be the sine of 150. So times the sine of 150, which is, I believe, a half sine of 150. I should know. But yeah, let me just write it down. Yeah, that's a half. So it would be 1/2, and times 1/2, that's 1/4. So 1/4 L times mg. And then the torque due to N1 will be 0, and the torque due to the force of static friction will be 0 because both of them are there. And so I say that the net torque equals to 0, and therefore what? I have one torque contribution from this, and that's negative, and then one torque contribution from there, and that's positive. So set them equal to each other. So I have 1/4 LmG minus that one, minus this one equals to 0, or just they are equal to each other. Magnitude, radical 3 over 2, and then the force of static friction times L. So the L cancels, and so here I would have mg over 2, multiply both sides by 2, will equal to radical 3 times the force of static friction, but the maximum force of static friction that I can have is mu s times mg. Okay. And so, oh, and gravity also cancels. So mu s will equal to 1 over 2 times radical 3. Okay. Which is 0.288. 0.288 or 0.29. Now, if you have if the force of static friction is less than this, it will slip. If it's greater than this, that's good. Okay? So that is the minimum force of static friction that you have. So yeah, when the force of static friction is maximum, you should not, you're about to slip. So that is the minimum force of the coefficient of static friction. All right, I will see you in the next video where we do rolling with rolling motion, where the axis of rotation is moving also, rolling and translating.